Okay, what we'd like to do today is last day of the class sessions is we want to talk a little bit about motion relative to rotating axes and then offer a little bit of course wrap up, and then that'll pretty much end the introductory dynamics course for you. So I think what might be useful is to start by going ahead and looking at motion relative to rotating axes. And let me show you a couple things in the book from the last section of chapter 5 that they'll give you an insight as to why we might want to do this. So if you look, page 410, and I'll try to come in a little bit more on these two problems. And I passed out to you the solution to these plus one other one. But what you'll notice is that you have, in both cases, a rotating body. You have a rotating body, and there is an object that is in motion on that rotating body. Object is in motion on a rotating body. We've done problems like this before, and the way we've done them is we've used a fixed axis system, an XY axis system that's fixed, an inertial, non-rotating or non-moving reference frame. And then we've written our equations that way. There's a more powerful way to do that for more complex problems. And what that is to establish an axis system on the rotating body and let the axis system rotate with that body. So I'll say that again. We establish an axis system on the rotating body in which there's something moving on it, and we let that axis system rotate with it. By doing that, it allows us to gain additional insight, and sometimes it makes the problem solutions a little bit easier. And again, this is mainly used in more advanced type of dynamics problems. So I wanted to expose you to it. I'm not going to make you tackle this on the final, since we're just touching on it on the last day of class, but it's definitely appropriate for you folks moving on into more advanced subjects next year. So I gave you a handout on that at last class session, and if you have that with you, you can just sort of follow along. And I'm going to go ahead and put it up here, and we'll see if we can talk along together on it. Okay. Is that legible up on the monitor? You folks see that all right? Okay. So we have to do some mathematics here. What was that?
Just said, oh.
You love the mathematics, I know. Okay. So, here we go. Notice what I did in the handout. Did everybody have their handout? Okay, good. Here's a non-moving axis system, capital X, Y. And imagine that there is a body, a rigid body up here that involves points A and B. And what we're going to do is we're going to etch on that rigid body an axis system, little xy, that travels with the object with its origin remaining at point B. And that rigid body might be in rotation. So relative to your inertial reference frame, there might be some theta dot and some theta double dot. Okay. Now, what we're going to allow happen is we're going to let, and we'll get to this in just a minute, we're going to let a point move on that rigid body relative to this point A. So what we'll do is we'll establish a point P that is on this rigid body that's coincident with point A, and then we're going to let A move away from P. Similar to what you saw on those two illustrations when we started a few minutes ago, where there was a rotating body and there was a pin that was moving on that rotating body. Okay, so here goes the math. So we write the position vector of point A plus, that's equal to the position vector of B plus the position vector of A relative to B. Now on the exam, last exam you folks took, some of you ended up writing the relative position vector backwards occasionally. Not too many of you did it very often, but occasionally it did show up. So you got to be very careful that you're the observer. If you're the observer here, you write your vector from here to the other point, not the other way around. So if we're going to use this local axis, this rotating axis system, then you can see that A is positioned at a distance x, y, using I and j associated with that for your relative position. You then, now we differentiate this, and this is going to take us back to something we did earlier in the course. So we're now going to get the velocity of A equals the velocity of B plus the derivative of xi hat plus yj hat. But I hat is in rotation. I hat's in rotation, so that time derivative exists. Remember back when we worked up our normal, tangential, and polar type of stuff, we had to worry about those unit vector time derivatives. So here we have the product rule applied. And stop me if you're confused anywhere, and we'll talk about it. Product rule here, product rule over here. And then, without going through the full explanation again, down here where my finger is on the left side, the time derivative of I hat is equal to omega j hat, where omega is theta dot. The time derivative of j hat with respect to, or excuse me, derivative of j hat with respect to t is negative omega I hat. Making that substitution for these time derivatives up here, we end up getting this expression. We then take a look at, we separate out the x dot I hat and the y dot j hat. We separate those out. And this other pair of terms, where let's see, I'll move my finger over here. These two terms right here is an omega cross r type of term right here. So these two terms, this j term and this I term, are created by an omega cross r.
So it's kind of like going backwards.
Yeah. Okay. So notice that this equation now, because of the rotating axis system, this equation where I have the pinpoint showing, is similar to what you've seen earlier. Here's what you've seen earlier, and we've been using pretty effectively. But we add on this thing to account for the fact that this axis system is in rotation. The terms in here, this is the point, this is the motion, this V, what we call V rel, or V relative, is, let's go up here and look at the picture. If you let this point A move away from that original spot, and we'll call the coincidence spot P, if you let that point move away, imagine it's got some velocity, like say in the direction of my pencil point. Okay? Wouldn't that have an x dot I and a y dot j? Okay, if that point A moved away from that original spot right there? Yeah, just like back on projectiles and stuff. So that's what this term is over here, is what's called VREL. One thing that you want to keep in mind, and I don't think the book emphasizes this, is when you start using this rotating axis system, every one of your terms, everything in your vector equation, everything there is written relative to this axis system. So you write all of these terms using the little xy axis system. You don't mix the axis systems together in writing part of this one way and part the other way. Now, little r vector is to abbreviate it, is the position vector of A relative to B. Now, if we let point P be coincident with A and then let A move away from P, in other words, imagine a plate that includes the points P, point P up here, and point B, and then let A start to move away from this point P, then we actually can break this velocity equation up into different components. This omega cross r term right here is the motion of P, the fixed point on this plate, relative to point B. And then this term over here, VREL, is the motion, is the velocity of point A as it moves away from point P. And if you like, on your handout, you can label up here, you can go ahead and put P right there, coincident with A. P stays there at that location on the plate, but A can move away from P. Okay. If you now look at these two terms, this is the velocity of point P. The velocity of point P, the combination of these two. Velocity of B, that gets you the speed of this point, and you add to it the velocity of point P relative to B, so that combination is the velocity of P. Another way of looking at this is to take these last two terms up here, and this is the velocity of A relative to B. Remember, A is moving away from P. But if you account for that motion, here's A moving away from P right here, and then if you have P relative to B, then that combination of these two velocity terms is the velocity of A relative to B. So there's different ways, you can see this nested structure here, there's different ways of looking at that description. You still awake? Okay. Now, oh, you know what happened? I was pointing down below here and it wasn't showing up there. But anyway, here's what I was just talking about. If you happen to watch this DVD someday. Okay. Now, we have to go further, don't we? So we need to take this equation right here that's boxed in, this velocity equation, and we need to differentiate this. So see if you keep your math hat on right now. And so we have to start cranking the derivative on this thing. And here we go down below. So move that up top. And if we look down below, now the acceleration of A is equal to the acceleration then of B. You now have two time-dependent vectors here in the cross product, and you need to crank their derivatives using the product rule, which you see down here, where my thumb is, and then plus the time derivative of VREL. What is the omega dot vector? That's theta double dot, isn't it? So that's the alpha, or the angular acceleration of the plate. That's the angular acceleration of the plate. What is our vector's time derivative? It is the time derivative of this position vector, which happens to be itself, and we actually did this earlier up above, this actually turns into a combination of omega cross r plus VREL. And then the last component of this is this thing, the time derivative of VREL. Well, the time derivative of VREL, look at how complex it gets. Okay, do you see the time derivative down below here? Again, we're going to have the time derivatives of these unit vectors showing up when we apply the product rule. So we crank through the details on that, separate out a couple of these terms, This term x double dot I hat plus y double dot j hat we call a rel. The other pair of terms, after you handle the time derivatives of the unit vectors, turns into this, which once again turns into omega cross v rel. So we take all this stuff down below here, and we place it now into this acceleration equation. Any questions so far? Still with me, or did I lose you? Lost a couple of you, maybe. Okay.
The handout really helps.
Okay. Let's now go to the next page. In your book, this is summarized on page 399. Okay, so here is a summary of how all of these acceleration terms sort of nest together. If you do all that substitution that was shown at the bottom of the previous page, we now end up with this acceleration equation. And here's how it all breaks up into these different parts. Now keep in mind, it's all written in terms of that little rotating xy coordinate system. Little xy coordinate system. And here are the parts. This cluster of here's an R alpha type of term, here's an R omega squared type of term, and what this accounts for is the motion of point P relative to that reference point B. That should make sense to you. It's got a potential tangential term and a potential normal term pointing back towards B. And orthogonal to it would be the tangential one. And then over here, these last two ones are a little tougher to understand, but what they have to be, if this is the acceleration of P relative to B, then this must be the acceleration of point A as it moves away from P. And it turns out to be this product and sum. And you can see that these two terms right here make up, in the nesting, that's the acceleration of A relative to B. Okay. The first three terms, if you grab a hold of those, this gets you the acceleration of point P. This is the acceleration of point P, all of this. Now, those details in that acceleration equation above are now shown in this sketch that I did down below here, and I think I'm going to try to zoom out a little bit so that you can see the combination of those features with that equation. I think that's probably adequate enough if it's still readable. I think that's readable. Okay. So here's, I drew these terms on here for you. So pointing from A, and P, remember, is locked in on the plate. Pointing from P and A back towards B is this omega cross R term that you see up here. Perpendicular to that normal is this guy, which is this alpha cross R term. Alpha cross R, which was shown up above here. Then the pin can move in the slot. Point A can move away from P in the slot, and it actually can have some relative acceleration here, or excuse me, velocity. Here's the velocity as A moves away from P, and a tangent to the slot, or the however the particle's moving on the rotating body, and it also could have a relative tangential acceleration term in that same direction. There also could be then that relative normal term over here, which is this 2 omega cross v rel, and this is always perpendicular to v rel, this term right here. And as I cautioned you at the very bottom of this figure, is you always want to make sure that you write that entire acceleration or velocity equation in terms of the little xy coordinate system. Okay. I may or may not have lost you on that. Now, let's take a look at problem 178 in the book.